Hi class, welcome to a continuation of our lectures on electrodynamics, and this is the first lecture for chapter 4. Our main reference is Introduction to Electrodynamics by David J. Griffiths, and again, this book is highly recommended for you. So for this chapter, we will first are going to be dealing with polarization. So this chapter is all about electric fields in matter. So there are many kinds of matter. We have solids, liquids, gases, metals. Woods, glasses, and each of them respond differently to electric fields. So say for example, we have two large classes of matter. First one is conductors and the other one is insulators, or we now call them dielectrics. So conductors are substances that are having a lot of supply of excess charges. These excess charge, they move freely throughout the surface of the conductor, and they actually do not belong to, the free electrons in the conductors are not tightly or is owned by a particular atom. They can jump from one atom to another. But this roaming around of charges are actually caused by external electric fields, or any electric field that could pass through the environment of the conductor. So for dielectrics, unlike the conductors, all of the charges are owned by or possessed by specific atoms. They cannot move around. So they respond to electric fields differently. And the charges, although they cannot transfer from one atom to another, they have all of the atoms in a dielectric participate in response to the electric field, external electric field, for example. Unlike conductors, where the free charges only moves within the surface of the conductor in response to the external electric field. By the way, there are two principal mechanisms by which electric fields can distort the charge distribution of a dielectric atom or molecule. It's by stretching and rotating. So when there is an electric field, what happens to the neutral atom in a dielectric is that they stay neutral because the charges are intact in an atom. But what happens is that there will be now a separation between positive and negative charges within the atom when there is an electric field that's passing. When you apply electric field on that atom. So when you have without electric field, the center of the atom, where the positive nucleus is located, is also where the concentration seemingly where the negative charges are also concentrated, are in the same place, the center of the atom. So when you apply electric field what happens is that the center of the atom and the nucleus would separate. So say for example, if you have an electric field going this way, so your nucleus, which is positively charged, would transfer to the left. In this case, because the electric field is going to the left. And the center of the the atom would still remain. And so this is now, you're now having a distance d, separation distance d, between positive and negative. So it's now, this is what we call polarization. So the separation of positive and negative charges in an atom, in a dielectric. So there is, what we now have is a dipole. So there's a separation distance between positive and negative charge, and they are equal to make the atom still a neutral atom. So when the field is large enough, they could ionize the atom. This means that you could really separate the nucleus and the electrons. Or even if you just get an electron from that atom by applying a large electric field, then you're able to ionize that atom. But with not so strong fields or less extreme fields, an equilibrium is established for these atoms by just by separating the positive and negative charges. So their separation causes a force which attracts the positive and negative concentrations of charges, and this holds the atom together with stability. So when you have external electric field, there are two opposing forces within the atom. The electric field E pulling the electrons and nucleons apart, and their mutual attraction between them together, they reach a balance. So that is your atom balances the electric field outside. And because of this separation of the negative positive charges, your atom is now polarized. So in that situation, your separation of positive and negative charges induces a dipole moment P of the atom, and this points in the same direction as the electric field. So depending on the strength of your electric field is also the strength of your dipole moment. So you have this is your dipole moment, is proportional to your electric field. So for different molecules or different atoms, you have different structures, and so the dipole moments created by the external electric field is also different. By the way, um, your alpha here, your alpha is called the atomic polarizability, and they depend on the structure of the atom. So say for example you have for the hydrogen, this is the atomic polarizability, and for the helium, for the lithium, for the beryllium, for carbon, for neon, for sodium, for argon, for potassium, and for cesium. So you have different magnitudes. As you can observe here, the atomic polarizability of gases is much less than the solid material. So by the way, in this table, your polarizabilities are determined by alpha over 4 pi epsilon, and the unit is cubic meters, and in the order of negative 10 to the negative 30. So let's go to the first example. A primitive model for an atom consists of a point nucleus Q, positive, surrounded by a uniformly charged spherical cloud, negative Q, of radius A. It's in figure 4.1. Calculate the atomic polarizability of such an atom. So here you have a very simple atom, or a simple molecule, just one atom. So in the presence of an external electric field, the nucleus will be shifted slightly to the right. So in this case, the electric field is going this way, and so your positive charges will move here. So since we only have a very weak electric field around here, we assume that the electron cloud stays spherically symmetric. So at that point, the external field pushing the nucleus to the right exactly balances the internal field pulling it to the left. So your external field is just equal to the electric field produced by the electron cloud, to balance the external field. So by Gauss law, and if you could look back to problem 12 or 2.12, you would be able to calculate that the electric field due to the electron cloud is just equal to this. You can solve by Gauss's law. So you can review the lectures on Gauss's law and be able to calculate that electric field. So at equilibrium, since the external field and the field produced by atom, the electron cloud, is just equal, so you have the electric field here, but we have defined the dipole moment to be Q times D. So our atomic polarizability is just equal to this. So you have alpha equal to 4 pi epsilon sub O AQ, and V here is just the volume of the atom, which is 4/3 pi a cube. Simple atoms behave differently from molecules because molecules have their own geometry, and so they polarize. Say for example, we have a molecule. It's a little complex compared to the simple atom, which is just one sphere, and for molecules you have so many spheres. And depending on the arrangement of the spheres, they're able to polarize themselves with the external polarize themselves with the external electric field. And say for example, some molecules, they polarize more preferably in one direction than in the other direction, or in some directions. So say for example, for carbon dioxide, CO2 for instance has a polarizability of 4.5 times 10 to the negative 40 coulomb square Newton coulomb square meter per Newton when you apply the field along the axis of the molecule here. But only 2 times 10 to the negative 40 coulomb square Newton per meter for fields that are perpendicular to this direction. So in this case, the polarizability is, there are two components. So here your dipole moment is, you have two terms: the atomic polarizability, which is perpendicular to the field, is not zero, and also you have polarizability, atomic polarizability in the field, parallel to the direction of the field. But then again, the carbon dioxide is simple because the arrangement of the atoms in the molecules is just a straight line. But for a molecule that is asymmetrical, the general relationship between dipole moment and the electric field, the external electric field, is that you have to construct a tensor, because in general you have an asymmetrical molecule, and the electric field could be also in the three directions. So your dipole moment in the x direction would be this. The dipole moment in your y direction would be this, and the dipole moment in the z direction would be this. So you will have a matrix that's looking like this. Looking like that to represent the polarizability tensor. So your P would be some matrix times the electric field. In the general case. So the 9 sets of constants here, this one, 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 these ones, constitute the polarizability tensor for the molecule. So for each molecule which is a different structure than the other, you would have a different polarizability tensor. Their actual values depend on the orientation of the axis chosen. So each structure has a different element, tensor element. But it is always possible to choose axes such that all the off-diagonal terms are 0. So you can, and you're left with only the non-zero terms in the diagonal. You can always choose that one. So we've discussed about a neutral atom which doesn't have a dipole moment initially, but the dipole moment was induced by the applied field. But there are molecules which have permanent dipole moments. Like for water, for example, H2O, they have a different structure compared to the CO2. And let's look at the structure. So you have here a hydrogen atom, and then 2 hydrogen atom, and then you have an oxygen atom, and they're arranged in this kind of geometry, like a V, where the 2 hydrogen atoms are separated by 105 degrees. So what happens is that the external field will create a torque on this molecule. So unlike the CO2, you have if the electric field is going this way, so it will not create torque, but here it will create a torque like this. So the external electric field will, say for example, pull the concentration of positive charge here, and then the concentration of negative charge here will be pulled this way. The dipole moment of water is very large. It's 6.1 times 10 to the negative 30 coulomb meter, and this is actually inherent to the property of being an effective solvent. By the way, water is called a polar molecule. So let us now calculate the torque on H2O. You have N. So the force on the positive charge is just the distance from the center, from the pivot point, across the force, and then the distance of the negative charges from the pivot point and the force acting on the negative charges. So all in all, you have N equals QD. QD is just P, which is this one. So you have a torque, and this torque is necessary in order to line up the dipole moments parallel to E. So N is in a direction to line up parallel to E. A polar molecule that is free to rotate will swing around until it points in the direction of the applied field. So there will be rearrangements of the atoms. So if the field is non-uniform, so that your F plus, the force acting on the positive concentration of positive charges, and the force acting on the concentration of negative charges does not balance, or does not balance exactly, so there will be a net force on the dipole in addition to the torque. So the formula for your force would be equal to this one. So there's a kind of difference between, or there's a difference in the electric field between the positive and negative ends of the molecule. So if we have a very short dipole, the small change in the electric field, say for example for the direction X, would be just this one. The same formula, the formula is similar for EY and EZ. So for all three directions, your difference in electric field would be this one here. So the force would be this, where your P is again Q times the distance between the charges. So all in all, altogether, so for a perfect dipole of infinitesimal length, the torque about the center would be given by this one here. So it's going to be two components, or composed of two terms: the torque due to the electric field, and the torque due to the forces acting on the concentrations of positive and negative charges. So again, what happens to a dielectric material if it is placed in an electric field? All of its neutral atoms, for nonpolar molecules, the field, the external field, will induce a tiny dipole moment for each atom, where the dipole moment is pointing in the same direction as the field. But if you have a polar molecule where the arrangement of the atoms are asymmetrical, each permanent dipole will experience a torque which tends to line them up along the direction of the field. At a higher temperature, especially when you have really high temperature, that would tend the atoms to move in random motion. So it's a different kind of situation. But anyway, if you just have some temperature that is not so high that um, the atoms are not going to be in uh, random motion. So anyway, the for both the polar and non-polar molecules, um, the external electric field would make the material polarized. A convenient measure to this effect is called polarization, which is just the dipole moment per unit volume. By the way, by the way, even if in some situations, even if the electric field is removed, there is some kind of um, freeze in the polarization. Like, say for example, as an analogy, if you have a material exposed to a very strong magnetic field, this somehow makes the material a magnetized one. So there's what we call an induced magnetism on the material, say for example. But in this case, it's electric field. We don't have the magnetic field yet. So we will discuss the magnetic field in later chapters. Now we go to the field of a polarized object. So in a piece of polarized material, there are a lot of atoms, and these are and the polarization, the dipole moment per atom is all throughout the volume. So you have a dipole moment per unit volume of the material, and that is called the polarization, because it's the entire material is affected by the external electric field. So question, what is the field produced by this object? It's not the field that may have caused the polarization, but the field the polarization itself causes. So you have in a material, when you have atoms with dipole moments, they have in general polarization. So what is the field caused by the polarization? So to be able to know, chop the material up into infinitesimal dipoles and integrate to get the total and work with the potential. So for a single dipole P, the potential is equal to this one here. So if you review your chapter 3, check which lecture is that, and you'll find out that the potential due to the dipole moment P is just equal to this one. So say for this material, for example, the unit vector R here is pointing to the direction from the dipole moment to the point at which the potential is evaluated. This is just the distance between them. In asymmetric molecules, the induced dipole moment may not be parallel to the field, but if the molecules are randomly oriented, the perpendicular contributions will going to be averaged to zero. Within a single crystal, most of the atoms are oriented in a single pattern. So the dipole moment P in each volume element d tau would be given by this. And so the total potential then would be this one. So if you compare this to this formula, so you're just doing this for one atom, and this one is for a volume element. The volume element could be could contain many atoms. So we have here from previous lectures, the del of 1 over r is just the unit vector divided by the r square. Of course, the differentiation is with respect to the prime coordinate. So you can rewrite 4.9 here into this form, such that when you integrate by parts, say, now we can integrate by parts so that we can rewrite this equation into this equation. So say for example you have del of p dot r, this would be equal to del the p 1 over r plus p dot del prime 1 over r, and this is just looking at this, this is just r over r squared, so that you can rewrite everything to this one using the divergence theorem here. Let me erase everything. You can rewrite this into this form, where this one here is just using the divergence theorem. You can convert this volume integral into a surface integral. You just rewrite this in the same way. So the first term looks like the potential of a surface charge here, and then the second term looks like a potential of a volume charge, as you may have seen in the previous lectures. So therefore the potential would be written that way as well. So we replaced the polarization that with the normal vector uh, with the charge distribution, bound charge distribution, and then you have rho, the bound volume charge distribution, which is just negative del of P. So instead of integrating the contributions of all the infinitesimal dipoles as in 4.9, which is just this one here, you have the bound charge. You can find the bound charge and then calculate the integral. And when you calculate the integral, this is much better, because like this one, you can use Gauss law or Gauss's law. So let's now go to an example. Now, find the electric field produced by a uniformly polarized sphere of radius r. So we have here a polarized sphere of radius r, and then we find the electric field produced by this material. So if we choose the z-axis to coincide with the polarization, so here is the direction of polarization, and the point is somewhere here, somewhere there, and so your P dot n would be, so this will form an angle theta here, so that it will be just cosine P cosine theta. So theta there is just the angle between the point and the z-axis, so you have there the theta to be just the usual spherical coordinate theta. So if you look at the example in 3.9, this would just be the same as a sphere with surface charge density coated on the surface of the sphere, say P for example, and so you will have the potential equal to this. The detailed calculation is discussed in chapter 3, so you can review it, take a look at it, and you can actually just compare it, and then you will just be able to replace this with a charge distribution K on the surface of a sphere. So since r cosine theta is z, the field inside the sphere is uniform. This is uniform. This one is uniform. Outside, it matters because of the distance of the point from the center of the sphere. So if you get the electric field, that would be just the negative del of the potential, and of course this would just give you this one for r less than the radius. So this is just like a very familiar form. So when you have a material, a conducting material, you would just have E here, or some charge, some charge, some charge density, some charge density, sigma. And of course, outside the sphere, the potential is identical to that of a perfect dipole at the origin. Then you would have this as the potential. But again, your dipole moment would be just this one. So you can just replace that. So this is what it looks like. You have a uniform field inside the dielectric, but outside you have multi-directional field. So that's it. What really are bound charges? This concept is limited to dielectrics or insulators. They are limited to the boundary of the dielectric. So say for example you have an arrangement of atoms in a straight line here. This one here. You can only see, when you polarize the material, you can only see the charges at the boundary. Say for example this one here, there will be an accumulation of negative charge here, and there will be an accumulation of positive charge here. In this case, you have bound charges when the material is polarized, but in between them is totally zero charge. I mean, the sum is zero, so you don't detect an accumulation of charge in this region. So there's no accumulation of charge in this region, but only at the boundaries, here and here. The bound charges also cannot be removed from the material because these are each electron, all of the electrons are tied or attached to a specific atom. So you cannot, unlike the conductor where you can remove electrons from the surface of a conductor, or you can add electrons on the conductor. But for the case of dielectric, the electrons are just there. You cannot get it. So they are thus called bound charges. So say for example, if you want to calculate the amount of bound charge resulting from a given polarization, let's look at this figure. So here you have a tube, for example, and this tube has circular ends, area A, and so if you take a slice of it, so you have here an accumulation of negative charge here and accumulation of positive charge here. So you will have a dipole moment QD, so that your charge distribution on the side would be equal to this. This is just equal to the sigma. So this one is Q equals PA. So For oblique cut, like here, the charge is still the same, but your area is already different, and so your sigma b would be this one, as in the case here. In general, but anyway, the angle would be the angle would be zero if it's flat. So theta here would be equal to 0, and thus your sigma would just be equal to p. So for the case in figure 4.14, the polarization is non-uniform. It is not only in one direction. So there will be accumulations of bound charge within the material as well as on the surface. So here in this case you have multi-directional polarization. So the positive charges are concentrated the positive bound charges are concentrated on the surface, while there is also a concentration of bound charges, surface charge here, inside the material. So the net bound charge in a given volume is equal and opposite to the amount that has been pushed out through the surface. The volume charge density inside the bound volume charge density would be calculated this way. By the reasoning that the net bound charge in a given volume is equal and opposite to the amount that has been pushed out through the surface. So you have here, as given previously here, given previously here. So that's it for bound charges. Now let's look at an example. There is another way of analyzing the uniformly polarized sphere, the supposedly uniformly charged sphere in chapter 3, but now we have a dielectric. So there's another way of analyzing the uniformly polarized sphere, which nicely illustrates the idea of a bound charge. What we have really is two spheres of charge, a positive sphere and a negative sphere. Without polarization, the two spheres are superimposed and cancel completely. But when the material is uniformly polarized, all the plus charges move slightly upward to the z direction, if the polarization is in the z direction, and all the minus charges move slightly downward. So you can exaggerately see that here in the figure. So all the positive charges are here and the negative charges would be here, and they're now separated by distance d. So the two spheres no longer overlap perfectly. So you have a cap of positive charge above and a bottom cap of negative charge below. And you can see here the bound charge. This is the bound charge above and the bound charge below. Bound charge is because you cannot get that from, I mean, you cannot get these charges from the material. So if you go back to chapter 2 and use Gauss law to calculate the electric field of two spheres uh, with opposite charge, the electric field there would just be equal to this, where d is the separation distance between the centers of the two spheres, and then the q would just be the charge accumulated on the upper and the lower surface of the spheres. So in terms of polarization, you can, of course, we have a definition of the dipole moment equals qd, and this is just, of course, for the sphere. This is just 4/3 pi r cubed p. And so you have E equal to this one here. So for points outside this sphere, for some points here, it will just look like a dipole at the origin. For point for some point, say Q, some point O here outside. And the potential of the potential outside would just be equal to this. So now let's look at the field inside the dielectric. So for example, a dielectric material contains an order of Avogadro's number of molecules. So each of these molecules has dipole moments, and the best way you can describe the dipole moments there is through polarization, where polarization is the dipole moments per unit volume. Outside the material, the dipole potential dominates overwhelmingly. You don't have to look at the inside of the material, because you just have the surface charge density of that material, and then you just use that to get the potential. However, if you go inside the dielectric, each of the atoms there have dipole moments, and it's very hard to ignore these dipoles. And so really we have to calculate it, but it's very hard to calculate that thing or that quantity inside the dielectric. So what we can do is just to average the quantity inside, average the electric field, the total electric field, because there's so many contributors to that electric field. Each atom is a contributor to the electric field, and by using the polarization, which is just the dipole moments per unit volume, an average can be calculated. Now, suppose we're going to measure the macroscopic field at some point R. within the dielectric. Let's look at this figure here. The true microscopic field must be averaged over an appropriate volume. A small sphere of about radius r can be drawn inside this sphere, say for example here, and then just pretend that this is a sphere and this is just r, and you can say that there are still a lot of molecule inside that sphere. So in this boundary, you will have two components of electric field. The one due to the outside charges and the other one is due to the inside charges. So here. So if you go back to chapter 3, the average field over a sphere produced by charges outside is just equal to the field they produce at the center. So the E out part is just the field at R due to the dipoles exterior to the sphere. So it is safe to use this formula for potential outside. Note that E is just equal to negative del of V, the electric field. So always remember that. So outside you have this can safely be used. Now for the inside of the sphere here, for the inside of the sphere in this area, you will have an average electric field. And if you go back to the discussion in chapter 3, the electric field there would be equal to this, regardless of the charge distribution within the sphere. But this one here, this one is also related to the polarization. The P, dipole moment here, is related to the polarization, which is just equal to this, which is just equal to this one, so that the field inside would just be this. So the macroscopic field then is given by in general this formula. So this is true for dielectrics, and the integral here runs over the entire volume of the dielectric. So there's a note here. The average field over any sphere due to the charge inside is the same as the field at the center of a uniformly polarized sphere with the same total dipole moment. This is very important. Although this section is not so not needed, not of so much importance, but it's good to know. The macroscopic field is independent of the structure of the averaging region where you're measuring the electric field, and this is of course derivable 4.19, which is this. So this is the formula of the potential. And remember that you can always get the electric field by this one. So for this session, I hope you've learned something, although it may be very complicated for you, but hopefully if you rewatch this video, you will understand more about the electric fields within the dielectric. So that's it, guys, for this session. So the next one would be watch out for the next one, I mean.